Here is a house. You know one thing about it. How big it is. No photos, no address. Can you guess what it sold for? A bigger house should cost more, but exactly how many more dollars per square meter? Answer that one question, and you understand the engine inside every AI. Last episode. Instead of writing rules by hand, a machine tunes numbers until they fit the examples we show it. Today we watch that happen in the simplest model there is. Across the bottom, the size of a house. Up the side, its price. Now in come houses we have already sold. Every is one real house. How far right it lands is its size. How high it lands is its price. These are our training examples. Follow the dots left to right. As houses get bigger, they climb toward higher prices. Our whole job is to capture that one climb as a rule we can use. But the dots do not sit on a perfect line. Two houses of the same size sold for slightly different prices for 100 small reasons we ignore. We are not chasing every. We want the clean trend through the middle. The simplest shape for a rising trend is a straight line. That line is our model, and it has a name: linear regression. It is just a formula from school. Price equals W times size plus V. Two numbers define the whole thing. Take W first, the weight on size. On the graph, it is the slope, the steepness of the line. For each extra square meter, how many more dollars? Crank W up and the line tilts steeper, price climbing faster as houses grow. Now B, the bias, the predicted price of a house of size 0, where the line sits on the far left. Change B, and the whole line lifts or drops straight up and down, never tilting. W sets the tilt, B sets the height. Right now these two knobs are a bad guess. The line sits too low and too flat, under most of the dots. Before we can fix it, we need to measure exactly how wrong it is. Take one house. The line guesses price, but it really sold up here. That vertical gap, guess versus truth, is the error for this house. It's residual. Then every det raises its own error stick. Now crush every gap into one score. Square each gap, drawn as a real square. So a gap twice as big counts 4 times as much, and the minus signs vanish. Average those squares, and that single number is the loss. Right now 0.91. Make it as small as possible. But which way do we turn the knobs? There are far too many settings to guess and check. So plot the loss for one knob, W. 2 flat scores badly, 2 steep does 2, 1 value in between scores lowest. Those scores trace a valley, and our line is this ball, partway up the wall. The ball cannot see the whole valley, only feel the ground tilt underfoot. So nudge W a hair to the right. Does the loss go up or down, and by how much? That change in loss per nudge in W is the slope, the gradient. The green line traces it, tilting uphill, toward more error. Uphill is worse, so we step the other way, against the slope. We lower the knob a little, and the loss drops. That is one step of gradient descent. Read the slope, step downhill. And the steeper the slope, the bigger the step. Now do it again and again. Read the new slope, step downhill. Read it again, step again. The ball rolls down the valley, and the steps shrink on their own as the ground flattens. Each step lowers the loss a little more. One dial sets the size of each step, the learning rate. Too big, and the ball leaps clean over the bottom and bounces up the far wall, the loss flailing instead of falling. Too small, and it crawls. We set this dial by hand. The model does not learn it. With a sensible rate, the steps shrink until the ball settles at the bottom. The ground here is flat, slope 0, nowhere lower to go. The knob setting at this spot is the answer. The W and B that fit our houses best. Now carry them back to the line. Same thing, now on the dots. Each downhill step nudges W and B, so the line tilts and lifts into the cloud. The error sticks shrink and the loss drains. 0.91, ticking down, all the way to 0.06. And it stops. The line threads through the middle of the scatter, the gaps as small as they get. That is learning, start to finish. Guess, measure the loss, step downhill, repeat until it stops improving. No magic, just turning 2 numbers to shrink 1 error. Now the payoff. A new house arrives, one the model has never seen. We know only its size. Find that size along the bottom. Rise to our fitted line. Read across. The line hands us a price. The book calls this a prediction, a learned line turning any size into a sensible guess. But a real house is more than its size. Bedrooms, age, location, each another clue. So we give every feature its own weight, its own slope. Price equals W1 times size, plus W2 times bedrooms, plus W3 times age, plus the bias B, same recipe, more inputs. And the weights are not equal. Size carries a heavy weight, pushing hard on the price. Bedrooms, a medium one. Age barely moves the needle and can go negative, dragging the price down as the house ages. The weights are what the model has learned to care about. Now the recipe. Multiply each input by its own weight. Size times its weight. Bedrooms times theirs. Age times theirs. Each product drops into the column. One clue's share of the price, scaled by how much that clue matters. Those products add up to 1.12 at the bottom. That weighted sum is the prediction. Multiply every input by its weight, then add them up. It is the exact same operation as our one feature line, just wider. And it learns the same way the line did. Take a weak weight and turn its knob up. That input pushes harder and the output shifts. Gradient descent just turns all these knobs at once, downhill, until the output comes out right. The knobs have a new name now, weights. Step back and look at what you built. Inputs arriving on their own wires, each wire scaling its input by a weight, all of them summed, plus a bias, into one output. This little machine has a famous name, a single neuron. As the textbook puts it, linear regression is a neural network with one single neuron. That neuron, the building block of every deep network and of ChatGPT itself, is nothing more than our house price line widened to take many inputs. There is a loose biological story, inputs arriving like dendrites. You just built the atom of deep learning from one line through some dots. So lock it in. The model is a line. Price equals W times size, plus B. The loss is the average squared gap from line to dots, one number for how wrong we are. Learning is gradient descent. Read the slope, step downhill, until the loss bottoms out. Widen the line to many weighted inputs, and it becomes a neuron. For ideas, all yours. But our neuron has one hard limit, so we stack it into deep layers, feeding one line into the next, hoping all that depth finally buys the power to bend. It does not. Work the algebra and two linear layers collapse into one. The weights multiply into a single new slope. The biases merge into a single new intercept, leaving W prime times X plus B prime. A line again. Stack 1,000 layers, still a line. The real world curves, and a straight line can never follow it. The fix is one small thing after each neuron, an activation, a bend. Add it, and the very same network can fit almost any shape. That bend is where we begin next time.